Okay, so welcome to TSTE27, lecture number 2. Last time we talked about basic transistor stages, and there was also some supplement material on how to calculate or derive the expressions, the typical expressions for a transistor. We had a transistor gain stage, I should say, gain stage. So we had typical parameters like the A0, the DC gain, the pole, and the unity gain frequency were important parameters, which is approximately A0 times P1. I argued last time that omega UG is a parameter which is typically hard to increase. It has a high penalty in terms of power consumption, and an option to increase the omega UG is to reduce the load capacitance, but typically we have a load requirement, or we have a certain load we have to drive with our amplifier. So we don't get rid of that particular capacitive load. So typically very expensive to increase the unity gain frequency. It's typically in the order of square root of the current. So if we need to double unity gain, we need to quadruple the power consumption or the current through our amplifier. And then we had this trade-off, gain bandwidth trade-off. So either you have high gain and slow system or slow low frequency pole, or you have a low gain and a high frequency pole. We're going to look into feedback today and just discuss the impact of feedback and the choice of CMOS gain stages in order to mitigate some issues with feedback. We will talk about ways to increase the gain. There are essentially 4 different ways. Last time we talked slightly more about resistive load. We'll just revisit active load and talk a little bit about current mirrors and headroom today and why there are certain issues with that. And then you had these typical electrical and physical design parameters that you can pull, current and voltage, but also the size of the transistor in order to increase the gain. And architectural choices. We can cascade, that is more or less putting stages in series or stacking them vertically. This is some sort of horizontal way of increasing the gain. This is a vertical increase of gain. We will see that the cascade is actually a sort of subclass of cascade shortly. And then we will add up with some more components like the differential pair, which you also recognize. We will do some extra calculations on that, which might be new for you, and then motivate why you want differential signals. And then with all that in place, we will have the differential pair, combine that with some sort of way here to increase the gain, to get a really high gain, and then we have operational amplifiers that we use in feedback loops. And then we're pretty set to use them in a switched capacitor circuit next lecture then. All right, so gain stages. All right, so let's revisit small signal schematics because that's always good to do. Previously we talked about the resistive load transistor gain stage like this, V in and V out. And then we added a capacitive load, CL, to that output, and we had a resistive load, RL. And that's an NMOS. And then it has its source connected to the common ground here. So it's a common source amplifier. We then argued that this RL is sort of evil character. It is typically physically big and it doesn't offer you much resistance. If it would offer you much resistance, which would increase the gain, that will also put limitations on the maximum current that I can deliver. Obviously, if that's mega ohms and that's 1 volt or whatever on the supply, the maximum current that I can push from supply to the output is essentially VDD divided by RL. So then it would be microamps, which is probably too small to charge this capacitor in a good way. So an option here was to go active, and then we put a current source at the top of our device like this, and then C load, and then we use a PMOS and an NMOS down here, so still grounded source, so still a common source device, but I replace my resistor with a current source which has a very high output impedance, more or less independent of the current, give or take. It's not really true because we have GDS lambda ID, so it's definitely dependent on the current, but it's a value which is, for its physical size, much larger than what it is for a resistor then. And the current that I can deliver to the output is sort of inherently given by the transistor itself, rather than here where you have a sort of RC dependency. Yeah, and then we added or could add a current mirror on the bias transistor like this. And this was also discussed in the supplementary material on YouTube, where we had some simulation exercises with multisim, which you have access to in your student accounts. So the nice thing here is that I get rid of design parameters here now. I don't really need to care about VF, W, or L for these transistors. If I have this current mirror structure, because I have the same source gate voltage on the PMOS transistors, and they have some sort of physical size ratio, the current more or less is a factor times this bias current on the output here. So if the mirror ratio is 1:1, they have the same WL on both sides. The current coming out on this side is also IB. So that's the sort of elegant way of getting rid of design parameters. So I don't really have to care about these two transistors. Otherwise, I would get a huge design space here then. WL, WL, VGS, VGS, current, etc. So that would give me additional 6-7 parameters. So that's a practical way of doing it. And now going back to our original equation here, ID is equal to alpha times VF squared. From this formula now I can see I have my bias current, and I have something related to the size of the transistor, and I have the choice of the DC voltage of my input voltage here. That's my 3 parameters that will control everything else. So boiling down this structure and sort of workflow to have parameters to pull here. All right, we also could look into some characteristics of this common source amplifier, which we'll use in the feedback discussions shortly. And we haven't spent super much time on that, but if we look at this architecture and do a small signal schematic of that, so let's practice that the first part of the lecture here. So I'll make a small signal schematic of the transistor on the left-hand side, like this. That's that transistor. The supply is grounded, so let's pull that like that. And then I have my other transistor, like a current source and an output impedance, like that, and then connected to my drive transistor, like this, and like that, and CL, which I could replace with a box, but let's write SCL like that. So that's my admittance for that. And this is now GN, this is GP, That's GMN times Vin in my small signal schematic. This guy is grounded. This is also GP. There is no current source here because small signal wise, the current source becomes open circuit. So it sort of disappears here. This guy is GMP times this voltage swing here. So that's being not 0 minus this voltage here, which is this node, Vx. And then this is my Vx here. This current source is GMP times Vx. So I'm assuming it's the same transistor sizes, so they have the same GMP also. And yeah, now we're pretty close to start to fold in this network. So this is my tip in general. If you do small signal schematic, just take the original schematic and then just plug and play the different components in your circuit. And then after that, you start doing the folding. We could take a look at this side for the sake of discussion. Here I have a GP. Here I have a GMP times 0 minus Vx. That's the voltage across this current source. And if you have a current source which is dependent on the voltage across itself, that's nothing else than a resistor or an impedance sort of. So this current source times the voltage across itself just replaces with a conductance, sorry. So we get here, this guy turns into GMP plus GN only. And just floating in the midair. This one we fall down and we get GP plus GN plus SCL, like that. And we also have yet a current source from the top. This is my V out. So this guy is GMN times V in. And this guy is GMP times Vx or 0 minus Vx. But what is Vx? That's this floating node here. And according to all possible laws, there is no current going here, which means that Vx must be equal to 0. So this is also GMP times 0. So from this sort of first order analysis, this current mirror does nothing to the small signal characteristics. If we take this one step further. So this guy just floats around on the left-hand side. The GMP times 0 does not accumulate anything from the current mirror side here to the output. So let's just continue. 3. So that boils down to a circuit looking like something we recognize. Sorry, this way. V out. And then we had GP, all those in parallel. Yeah, the GM disappeared. And then this is GMN times V in. And then we get V out divided by V in is equal to GMN divided by minus GMN GP plus GN plus SCL. So that's equal to some sort of transfer function AC of S equal to minus GMN divided by GP plus GN divided by 1 plus 1, S divided by GP plus GN divided by SCL, All right. So we're going back to the basics here to be prepared for what we need to do next. All right, so resistive load, big and evil. We need active load. We control the active load with the current mirror. We conclude that the current mirror does not add anything to the right-hand side. So this is sort of isolated from the actual gain circuit, which is here. We can do the small signal schematics, and we see that we get GP plus GN. Previous time we had something like RL or GL here. We write it on Bode's normal form, BNF, and that helps us to identify the gain, the DC gain A0, yet again here. And that's our pole P1. All right. And also, since this is a single pole, single stage, single pole amplifier, that implies that this GP plus GN is also equal to the output admittance or conductance. So we have some different parameters here that we can compile. So just sort of standard forward calculations here. Okay, let's then sort of compile. So A0 is minus GMN divided by GN plus GP. We have G out or R out is equal to 1 over GP plus GN. And we have that R in is equal to infinity because we have a gate at the input signal is connected to a gate of a transistor. So there is no current going here, that's 0. So the input impedance has to be infinite. And then the pole P1, the dominant pole, is 1 over R out times C load, like that. All right, so for the common source stage, we have phase shift, 180 degrees. We have a high number. GM is a number which is much, much larger than GN plus GP. It has to be, otherwise the transistor wouldn't have any gain, so it wouldn't make sense to use it. Rin is infinite. The output impedance is pretty high. So GP and GN are small numbers. So R out is a high number, which means that P1, which is 1 over a large number, so that's a small number typically. So we have something like this, P1, A0, sorry, not at all A0, here's A0. So we have a system with pretty high gain, but also low frequency pole. All right. So let's just continue that further, this discussion. We introduce something we call the common drain stage. And once again, this might be material you already looked into, but I want to develop an understanding for the different building blocks we have in our CMOS world. So common source, we have concluded and made a table. We'll come back to that shortly. Common drain, I can put two transistors like this and put the capacitive load. This is a bias current source. And always you should bias this with a current mirror like this and use a current source to supply this amplifier stage with current. So that aside. And then I put my input signal V in here and my V out here. We will not do any small signal schematic calculations on these guys. We don't have time to do for all of them, but it's well covered in the material. What does the common drain do? Well, actually, if you look at it, there is a current source down here, which produces a current, constant current, more or less, give or take, at least from the first order concept, because this current mirror makes sure that we have the same gate source voltage on that transistor. If I have a current here, which is constant, and this transistor has its simple equation that we should know by now. It's I equal to alpha times V in minus V out minus VT squared. That's the voltage from that point to the output. That's my effective voltage of that transistor. So that's a constant. That's a constant once we have designed properly, and that's a constant. So obviously V in minus V out must be constant. And if we look at the maths here, if I want to do a derivation to find the gain, I notice that A must be equal to 1. So if I put V out equal to a constant plus V in, and I do A is equal to dV out, dV in, that's simply going to be 1 according to all possible math rules. All right, so now it's quite nice because from this number I know most of the stuff I need to formulate the transfer function for this device. I know that the gain is 1. I know that my driver transistor will have a transconductance of GM. So I can directly from this conclusion set up a transfer function A of S equal to, I know my drive transistor has GMN divided by G out. I know I don't need a minus because I see that V out is equal to constant plus V in. So this derivative is going to be positive larger than 0. So there's no phase shift. And then according to Bode's normal form, I know that this has to be G out divided by CL. And yeah, so from this previous equation here, we could also have identified that G out is visible here in the numerator of that expression. All right, but I know that gain has to be 1, so I know that this factor has to be 1. So G out must be equal to GMN. So it's a quite good way to just, I'm just showing you some thinking that you can do like an analog designer to sort of derive all the parameters just by looking at some simple basic facts about this circuit. Single stage amplifier with gain equal 1. Okay, so with that said, we can formulate the same things as before. The input resistance is infinite here. This is going into a gate. R out is equal to 1 over GMN according to this conclusion here. A is equal to 1 and R out, P1 is equal to GMN divided by CL. Now suddenly we have a case with a low number, low gain, but very high bandwidth type of circuit. Okay, so we looked at common source and common drain. It's called common drain because the drain node here is connected to AC ground at the top here. So let's look at the last building block before we combine them. All right, so that's going to be common gate amplifier. So the gate is now going to be grounded. So we have a current source at the top and a transistor NMOS with the bias voltage here now. And the bias voltage, another bias voltage on the top. This is a PMOS. Here I have my output capacitance, SCL. Here I now put my input signal. Both these guys would then be generated through current mirrors. I'm not going to add them here now, but that would be the normal way. So this one acts as a current source. Current source, which will produce a current, constant current, more or less, or at least a bias current here. And then we have something happening down here. But if you look at it, here, this is the gate source voltage of this transistor, going from a AC constant to a moving input voltage. That's very similar to our common source circuit here, where I have a moving signal V in on the gate going to a constant voltage on the source. So it's essentially doing exactly the same operation as the common gate. It's just that I had sort of flipped them AC-wise. So this is just flipped compared to common source then. And that means that I also here quite quickly can just conclude everything. So looking in at the node here, it looks very similar to common source. So let's just conclude that R out is going to be 1 over GP plus GN. The small signal schematic will look very similar. A naught will be GMN divided by GP plus GN without the minus. Okay. And then we will have R in being a small number. It's not necessarily small per se, but it's at least less than infinite, unlike the other cases. Why is it less than infinite? Well, obviously we can throw in a current here because this current has to go somewhere. So there is a current going from the input voltage source into the transistor here. And P1 then, well, that's simply the same as for the common source. So it's GP plus GN divided by CL. So also here I have a case which has high gain A naught and a low pole P1. But I also have a resistor here, input resistance, which is non-infinite. All right. So a quick guide through all the different building blocks that you have available as amplifier stages. That's essentially it. These are 3 different ways to connect your transistor. If you think about it, the transistor has 3 terminals. So I can sort of relate my input voltage or the variance of my effective voltage on the transistor to in three different ways. So I ground my source, I ground my drain, and I ground my my gate. So what are the implications on these then if I want to increase the gain? So let's start talk about that and see how much we get before the break. So how to increase gain. And why do I want high gain to begin with? Well, it's in my feedback loop where you have some sort of system, you know, in the end, from control theory, we have some beta feedback factor to an amplifier, and you have V in here, and you have V out, and you have a minus, and you have an epsilon, and we have a transfer function V out divided by V in equal to well, it's approximately equal to 1 over beta is the end result we want, because we want to make the device independent of variations in the gain of the amplifier. So, sorry, I had to close down a bit. So this is the desired. You want to make your feedback loop independent of the amplifier itself due to tolerances issues. So beta is typically a sort of passive network consisting of resistor or capacitors, which have a better matching than your transistors will have, because these will vary quite a lot with temperature and voltage and what have you. So if A is infinitely large, this holds. If this is perfect transistor with a, you know, a transfer function which is A being infinite for all infinite frequencies, this loop will work and produce a desired result being 1 over beta. If this is not perfect, remember from control theory, if we have a transfer function like this in the loop, if this is my beta times A of S, this is my loop gain. And I have started adding poles P1 and P2 in my loop. Normally also you typically set beta equal to 1 to be on the safe side. So normally you perhaps only consider the gain of the amplifier itself in these type of systems. And then we have one dominant pole and then a parasitic pole. And we might remember from control theory then that the issue is that each one of these poles will pull down the phase response by 45 degrees. So at P1, I will have dropped 45 degrees. We will come back to this after the break. 45 degrees, and for P2, I will also pull down 45 degrees. So in total, P1 will pull down 90 degrees once it's sort of done. And then we get to P2, which will also pull down 45 degrees like this, and continue down to minus 180 degrees eventually. And then you remember from control theory that we define the phase margin. And now I put them so close to each other, so we don't have much phase margin, but down here we have phase margin, which is being the distance in the phase shift to the 180, the dangerous 180 degrees here. Okay, so we need to guarantee a certain phase margin. This is still stable. If phase margin is larger than 0, it's still going to eventually tune in and give you a good number out. But the less the phase margin is, the more, you know, swinging you will have on the output voltage. There will be some settling behavior, which will depend on the phase margin. So the number of fluctuations around the sort of n value will be a function of the phase margin. And we typically design them to be 45 degrees, or more conservatively 60 degrees, which will then give you a quite nice settling behavior like this. Once again, we will come back to this when we discuss switch capacitor blocks. I just wanted to give a very quick background here before the break. So from this feedback background, it is sort of obvious that we have to increase the gain of our device in order to get a desired function. Revise your control theory books otherwise. The gain in the ideal case will have a frequency response which is infinite for all frequencies, but in reality we will have due to the dominant and parasitic poles, we will have a spectrum that is not infinite for all frequency, and in fact it's so poor for a certain frequency above this omega c cutoff frequency, where you don't have any gain at all anymore in your amplifier, and that means that this loop doesn't behave at all as you want. So that's just the motivation, and then we will come back to discuss this further after the break. So I'm going to resume. All right, so welcome to the second half then. We concluded we need higher gain. So what are the options? Well, perhaps quite obvious. I can take a common source, and connect that in series with a common source. So if I take two amplifiers like this, and you know, from a transistor point of view, it could be done in many different ways. Well, not many, but 4 different ways. If I like, I can take these two common source stages like this, and dependent on what I want to achieve as a closed system, I could, for example, put my input signal here, and I can take the output and connect that to common source stages, and I can connect them like input and this output to this transistor to that transistor, and I can take the input here and connect, also choose where I want to connect. It's nothing, you know, we didn't say that before, but obviously we don't need to have the input signal on the NMOS. It could be on the PMOS instead. We have just flipped our reference frame upside down then. But for sake of argument, let's assume it's connected like that. And then typically you would probably connect the biases here, and you would probably connect the current source here. And then you would have through the current mirror, have a bias source. And once again, we could have a mirror ratio here, we could have a W here, and you could have 2W here, and say 4W here. And then I would get twice the current here, and I would get 4 times the current here. So this current mirror acts like a current amplifier, i.e. an amplifier. All right, so that's one obvious way of doing it. Let's look at the other way, just to be able to compare them shortly. This is the one we call Cascade Amplifiers.
Hello?
Yep, so Cascaded Amplifiers. I have one stage connecting with a high input impedance to the next stage. So they are sort of isolated from each other. They are cascaded. So R in of second stage is infinite. So then it's sort of cascaded. All right, so let's look at the alternative, or one of many alternatives, I should say. So I could take a common source and I can connect it to a common gate like that. What's the implication here? Well, perhaps a bit cryptical, but the end result would be this. I would have two transistors on the top, another transistor, and then my last transistor at the bottom, like this. So this is a PMOS, PMOS, NMOS, NMOS. And I would probably connect to some sort of capacitive load. And I would have V out here, and I would have V in here, and I would have V bias 1, V bias 2, V bias 3 on the different transistors. And then in fact, it's this guy down here. That's my common source. I have my source voltage grounded, small signal wise. And then if you look at it, this guy up here, that's my common gate. So I have connected common source with a common gate. I need two transistors up here in order to increase the output impedance of this current source in order to guarantee high gain. So we could add that as a comment. Obs. Symmetrical symmetry requires two transistors here. So if I don't add two transistors here, just one of them, the output impedance, if I look up this node, will be only dependent on one single transistor, which will not match. If I go down this way and look, then the output impedance will be dependent on two transistors in series. So in order to balance the amplifier, I need to have two in series at the top here. That will increase the output impedance and guarantee high gain for me. So we will come back to that also. All right. Okay, so that's cascaded case then. And that means that R in of second stage is less than infinite. So if I look in here, the input impedance of this node is low. Well, it's considerable. It can be high, but it's not infinite. And we will come back to implications of this shortly. So we have two cases. So let's look at the third case. So common source in series, common source, common gate, and then the third case, which I just hinted before. So like we said, if I take, let's for the fun of it, draw them like NMOS. So if I take a current mirror that we use for biasing of our current sources as active loads in our amplifiers, like this. And then we have an input current here, I. And then I have an output, I out, I in. These are both NMOS. And for this guy, let's say it's W1, W in perhaps, W out, And we assume they have the same channel length L. Okay, so this means that I in is equal to alpha in times VF squared. And this effective gate voltage is the same on both transistors. So we also know that I out is equal to alpha out times same VF squared. And then I can derive or divide both the equations, and I get I out divided by I in equal to alpha out divided by alpha in equal to W out divided by W in. So I amplify the current by a factor dependent on whatever W's I've chosen here. So we call this CM, or current mirror, because it can amplify the current and also act as an amplifier. And we will look into that use of that shortly. So yeah, so I could, for example, use a, I could have a current, so common source to a current mirror basically, and then some load of some kind, for example. That would give me gain then. So I will have gain in my common source, and then I can amplify the current, and I can terminate it over a load to get an output voltage. Or once again, I could terminate it over an active load also. I could put the transistor here acting like a current source at the output, and that will also give me high output gain then. And there are other ways to combine all these blocks. Maybe, we could also do like, I could take a common source and common source to get high gain, and then I might want to have low output impedance. Then I can connect the CD to get low output impedance, low, R out, high, etc. So dependent on my application, once again, dependent on what kind of load I want to drive with my combined amplifier here, I might put a common drain at the output to decrease the output impedance if I want to drive low resistive loads, for example. If I have high output impedance, this acts as a current source. Current source. If I have a low output impedance, it acts like a voltage source. So if you go back to the fundamentals of electrical circuits in the Norton equivalent, for example, and the Thevenin equivalent, the current source has ideal and output, which is output impedance, which is infinite. And the voltage source has an ideal output impedance, which is 0. So that's different ways to combine them in order to mimic certain behavior of the amplifier, dependent on your load. So common drain typically sits at the output, always more or less. Output. Common drain more or less always on the output. Okay, so let's look at this. Common source is one option. Common source, common gate, common source, current mirror combination, for example. So let's try and see what we can conclude from these 3 cases. What could be positives and negatives of that? So number 9, let's assume we have the common source combined with the common source. And yeah, it will have a capacitive load like this. Well, we do have potentially a problem, dependent a little bit on the size of this capacitor here. But just assume for the sake of integrated circuits, then it's quite likely that this drives another integrated circuit. Okay. It's also likely that the transistors of this common source stages are pretty large because they want to generate the high gain themselves. Even though I cascade them like this in order to increase the gain, they will also have themselves quite high gain. So let's just look at this first stage here. So it's probably going to have pretty high gain A0 for the first stage. Let's call it A1. And then we have P1 with a Roman 1. So that's my first stage, and the second stage will have maybe pretty similar. So this will have A2 Roman and a P2 Roman like this. And then I combine them. So that's going to be the multiplication of those two because they are in series, equal to, and then I will get, a naught total being a Roman 1 times a Roman 2. And then I will have P Roman 1. And then maybe P Roman 2, quite close to each other. So this is sort of, a potential issue. We don't know where P1 and P2 are. I mean, from this system as I've drawn it, we have a slight capacitance here. If we look at it of our transistors, here, it's essentially the capacitance which is here. If you remember from the first lecture, the transistor operates as a capacitive load, more or less. It's the COX in the oxide layer here, which helps to set the current through the amplifier transistor. So this means that whatever this guy sees, he sees also the load from the gate of that transistor. So if we assume that this drives a pretty large transistor, that capacitance is going to be pretty large. And then we also assume that it drives another integrated circuit, which probably will be something like a CMOS device. And then this capacitance is in par with that capacitance, give or take. But we don't know which one of these two guys is the biggest. So we don't know P1. We don't know simply if it's equal to the dominant pole with the Arabic numeral. P2, so that's a question mark still. So we have to dig into that further later down the road. But obviously we see the issue. Poles too close, probably. Because, like I said before, we typically want something like the cutoff frequency to be close to this P2 pole. So the issue with cascading stages is that the poles become too close. Okay, so let's look at common source to common gate. Like this. So, well, do we need to, yeah, maybe we can draw, let's just do this again, even though it's a little bit overkill. So I take my transistors like this, that's PMOS, PMOS, NMOS, NMOS, and I take my output here, like this. This is now my first stage, common source down here. And this guy, however, sees a low impedance node here into the gate here. So R in here is less than infinite. Small signal wise, it still sees the same CGS of this transistor. If you remember, this is my common gate, and we had just flipped more or less the direction of the polarity of the driving signal compared to the common source. So the same thing for the capacitance, it doesn't change. Whatever capacitive load I see for a common source, I see the same type of capacitive load for a common gate. But I have an R in here which is less than infinite. Could still be large, but it's less than infinite. So that means if I compare these two guys, so I'm going to have A1 from my common source, the gain of this transistor. I'm going to have my pole of this transistor, which is dependent on the load here then. So here I have P1. And then in the other stage, the common gate, I will have pole P2 being associated with the output node, and that capacitance and the impedance here. So in this case, A2, and then I will have a P2 here. And these are combined to give me a combined. And now actually I'm pretty certain that P1 will be higher up in frequency and P2 will be very low in frequency. It has a high output impedance and it has a capacitive load. This has a low impedance associated with this node. So I'm pretty certain that AI times A2 will give me a P2 here, and probably, and now I'm exaggerating a bit here, but say P1 is up here. I'm pretty certain that P1 is much larger than P2 to separate the poles from each other. That's not necessarily the case, obviously. There could be a very low capacitive load here, for example, or something like that. We don't really know. No. But it's a fair assumption that they have more well-separated poles. So probably this structure is much easier to use in a feedback loop due to its inherently well-separated poles here, which if P2 is far away in frequency, it will never start pulling off the phase curve before we have reached the omega C. So if we can push P2 away, we will get the better stable system. So it's quite likely that the common source common gate, the Cascade case, has a better feedback property. However, as always with analog design, it has the issue of eating up the voltage range. We're not going to do many calculations here, but it's quite obvious. You have 4 transistors stacked on top of each other here, unlike the common source case where we have only 2 transistors. So if I want to turn on this transistor, I know that I have to, at least have a threshold voltage here, and that will give me a certain voltage here. I don't know, just let us invent 200 millivolts for sake of, not milliwatts, millivolts for sake of argument. And then I also know that this voltage, in order to turn on that transistor, has to be yet the VT, but also an additional 200 millivolts here. So I have like VT, this voltage here has to eat up more voltage range, etc., etc. So voltage headroom is suffering. For the common source to the common gate. In the common source to common source, we don't have any issues with voltage range. We have the minimum number of transistors stacked on the top here, on top of each other here. So this is essentially the best you can get. And I could stack more transistors on top of each other here and I would get even higher gain. For example, I could stack 6 transistors on top of each other, which would essentially be a common source to common gate to common gate. That would give me really high gain, but it would eat up the voltage range even more. And in a modern process, we have only access to maybe 1 volt. And it's quite obvious that this is probably like the maximum you can actually obtain for transistors, to be honest. So inherently faster or inherently, easier to compensate or bring into the feedback loop, but it's up to voltage headroom. It has another advantage. The current that goes through this branch is just one single ID. One current ID required through all transistors to give me the same gain. Whereas if I go back to this case, you have two branches, which means it has to consume current in both of these branches. And it might be that this requires a larger power consumption because we need more current to drive our circuitry. So less I, and the other ones are just vice versa then. So this sort of helps you when you design your operational amplifier. So we will you will look into the tables and to the graphs or figures in the PowerPoint or PDF to see the comparisons. But typically, why have people chosen these different ways of doing it? All right, let's take another one before we start talking about compensation techniques. So we had one third case, for example, common source to a common mirror, current mirror, sorry, like this, and then some sort of active load. Something like that could be done. So let's just see what that gives us. My pen is getting, see what this can do. All right, so common source, I want the common source transistor at the bottom. And once again, we can always flip back and forth PMOS and NMOS. So here I have my input signal. And now I put the transistor here, which is connected like a current mirror. And then I have another. And so now I'm here as that node. And as we see now, it's an output current coming here, but it's not terminated anywhere. So we have to convert this into voltage. And there are different ways we could do that. But obviously, something like this would make sense. A bias voltage, like an active load. So one could argue, of course, a slightly, what do you call it, philosophical way. One could argue that this is a common source with an active load connected like this type of diode fashion. And one could argue that this is a common source also. So arguably this is common source to common source. If we want. The difference, however, is that we will see a low impedance node here at the output of this transistor. This one we talked about before. If I look at the small signal schematic of this guy, we had a current source like that and the output impedance like that. This has a CL, sorry. GP, and then this guy was GMP times the voltage here. So 0 minus Vx, we called that one before. And this is exactly 0 volts here and Vx volts here. So that's a current source dependent on the voltage across itself, which is nothing else than a resistor or conductor. So this is equivalent to GMP and then parallel with GP. And that's approximately equal to GMP. And we know that GMP is much, much larger than GP. So that tells us that this pole is quite high up in frequency. if you think about it, this guy has a capacitance here, and then I have a output impedance, or the impedance load I see at this node is given by GM rather than GP. So that means that this pole is much higher up in frequency than the other cases we looked at, or at least the first case we looked at. So this is another option. So I don't know if I need to draw the diagrams, but let's just let's combine them already. We already done those multiplications, but so I'm sort of deliberately drawing it somewhere in between. So P2 probably, let's put larger than, but not necessarily much larger, but at least some decent amount of larger than the other one. And voltage headroom is fine. We only stack 2 transistors at the top of each other. So voltage headroom is okay. And separation of poles is okay-ish in comparison. All right. In the project, you will look at the current mirror approach here. So it's good for your report to understand what's happening here and motivate it well. And also you are going to derive the transfer functions and stuff for these. All right, so 3 different types of amplifiers. This is called a 2-stage amplifier, 2-stage operational amplifier you might have heard of. This shows up as a common gate, either a telescopic amplifier or a folded cascade amplifier. And this turns up as a current mirror operational amplifier in the end. So 3 different types of amplifiers with 3 different characteristics according to the discussions I've given you here. Some of them have improved voltage headroom, some of them have improved frequency characteristics. And that's why you choose them, more or less. So they have a purpose, and it's quite easy to understand the purpose if you look into this discussion here. Okay, so let's start wrapping up here. Let's see how far we get. We need to give a very quick discussion on the fact that the amplifier in my feedback configuration has to perform a difference operation at the input. So here I have beta, the feedback factor. Here I have A like that, and here I have my epsilon. And this performs a difference operation between the feedback output and the input. And that has to be implemented somehow. There are different ways of doing that. The way we do it when we compare voltages in the feedback loop is with a differential pair. So this is also probably known to you from previous courses if you looked into CMOS or bipolar. And I simply connect like this. Okay, so that's my input. V in positive, V in negative, and the bad pen, so let's throw it away. All right, so I could have done this some way. Just connect them to 2 common source stages like this. However, if I just assume that I want for a differential purpose, a differential pair, just sort of double the branches. So I could like take a positive branch and a negative branch and somehow mix them together and compare them. That wouldn't really help me because I'm not suppressing this sort of common mode signal. I'm not suppressing the common denominator of these two inputs. I have to do that somehow. I have to glue them together in order to create this difference operation. And I'll do that with a current source at the bottom with a fixed current. And then I get an IP and then IN currents coming out here. And then if I want to, I could take this differential input pair and I could connect them to a current mirror like this. And connect them like this. And then the glue current at the bottom. I can record a supplement video about this glue current and the effect it has. But it has it's required to be there more or less. And then I out here. So here is the nice feature. If I have IP and IN here, the current mirror will do its job. So it will make sure we have IP here due to the mirror ratio. And if I have IP coming here and IN being pulled here, we can see that according to Kirchhoff's law, this is IP minus IN. So I get the difference operation. So this is the basics to create the input difference operation of your amplifier. So at all amplifiers, you need a differential pair at input. And then you need to decide what you want to do with the load here. If you look at it, these two transistors together with the current source, that's your first common source stage at the input. And then you add some sort of current mirror load at the output. So concluding, current mirror amplifier, and now we call it operational amplifier because we have increased the gain to something which could be dramatic. And I will not have time today to talk about the pole zero separation, but you will find in the lab, in the project, that it's not really needed for the current mirror amplifier in your project. So it's not much that we miss, but I will record another video to clarify that a bit together with this PDF material that you have on your the one I talked about before. So we can go through that in a separate video. All right, so current mirror amplifier. Okay, we connect the input differential pair, current source, that's a single transistor more or less, nothing complex. V in positive, V in negative. And now in the current mirror case, I connect both output branches to a PMOS current mirror like this. And once again, this is available in the handouts. So a better picture is given there. Okay, and then load capacitance. So I put two current mirrors at the top here. So whatever current I have here, IP and IN, is now mirrored with a certain ratio 1 to K, for example, and a certain ratio 1 to K, dependent on the sizes W and L for these guys that you pick. So these are all PMOS at the top. So here I will obviously have K times IP, and here I will have K times IN. This is some I naught. All right, and I want to create a difference current. So whatever comes out at I out here, I want to create something which is the difference between current. So this has to be KIP then. And how do I guarantee that? Well, I guarantee that by adding a current mirror also here to the other transistor. So PMOS. So both of these two transistors have the same VGS at the bottom. So whatever I mirror at this side, I get also at this output, and then this guy will be K times IP minus IN. And there is a minus in this particular case, the way I've drawn it. I should have flipped the names here, would have been more logical. Okay, so this is your first operational amplifier, the one you will work on in the lab, in the project. We have a common source stage here. We have some sort of load giving you some sort of gain. The current is mirrored and then terminated on the active load. So once again, one could argue it's a common source plus a common source. But the good thing is that the poles are separated. And if you want to find the poles, say from input to output, it's quite easy. You just follow the track from input to output in order to identify where they could be. So this is my input signal. So I would sort of take, this would be my sort of signal path to the output. And then the trick is to identify what gates I encounter on my path there. So first I encounter this gate, which has a certain capacitance. Oops, you don't see that in your picture. This has a certain capacitance. And dependent on what impedance I have on my driver on the input, I will get the pole here. So dependent if I have some sort of resistance in my driver circuitry, I will get an RC time here. And then I continue, and here I bump into a gate. So here I will have another pole that will influence my frequency curve. And that pole will be given by all the capacitance I see in this gate, sort of this connection. So you have to sum up everything associated with this wire more or less. So that will be the CGS of this transistor, will be the CGS of that transistor, and whatever parasitics I might have connecting here and there for some extra stuff. So you know that this here will be something like 1 plus K times something Cox blah blah times some sizes, etc., etc. And then you continue. Okay, you go to the output, then you have your final capacitor, which will give you a pole also. So in this particular case, if we have a good voltage source at the input, we can ignore that one. We bump into one pole here, and then we bump into one pole at the output also. So it's a good way to take any circuitry and just go through the signal path from input to output and identify whatever you might bump into. All right.